Hi everyone, welcome today. Almost one of the last sessions, I think. I hope everyone had a good lunch and recovered from last night as well. So today we're here to talk about encryption, and we're also here to talk about machine learning and detecting malware in encrypted traffic using machine learning. So those are sort of the topics that we will be discussing today. So before we start, I wanted to make a small statement. Encryption is good for privacy. However, it gives challenges to other aspects of security. Contextual flow data is here to help. So even though I very much value encryption and my privacy, it also makes certain things more difficult. And throughout the session today, we'll have a closer look at that. So I'm not sure if people were in my session yesterday, but then this slide is the same. I just copy-pasted it. But who am I? My name is Christopher van der Made. I'm half Dutch, half American, but I'm born and raised in the Netherlands and lived there my whole life. I currently live in Rotterdam. I've studied in Amsterdam, did a couple of things on Science Park at the University of Amsterdam. All are very much focused on programming and on information sciences, which is one of my passions. I joined Cisco straight after university 7 years ago in a graduate program, which they call, where you become an associate systems engineer. I then was a consulting systems engineer focusing on security in a Northern European team. So I basically saw all kinds of different customers, help them build a security architecture and help implement certain things help them make their environment safer. So I did that for 4 years. And then 2 years ago, I joined the developer relations program in Cisco, or also known as DevNet. And I'm there in a role as developer advocate, focusing also on security. So basically, anything that has to do with Cisco automation and Cisco's security portfolio, that's where I'm involved with. All right, so enough about me. Let's have a look at the agenda. Quite bright slide here. I hope everyone's awake now. So first of all, we're gonna do a quick rundown of how encryption works. I assume most people will know it, but I'm going to cover a couple of small things which are important later in the session. It's always nice to get a little bit of a refresh on specific protocols. We'll then have a look at encryption and malware. Are they best friends forever or not? Then we'll dive a little bit more into the actual topic, and that is basically how you can decide when you're looking at encrypted traffic, which traffic is benign or safe, and which traffic is malicious or bad. We'll also go a little bit under the hood of an open source project from Cisco, which everyone here could use if they would like to, and we'll have a little bit of a look how the project actually works. All right, so how does encryption work again? So this is going to be a 101 session, but very, very briefly, when you take the paint example, when you're doing a key exchange needed for a secure channel later, so you want to exchange a secure key to create a common secret which you can use to start an encrypted channel, for example with TLS. So very simply, if you look at it this way, Alice and Bob want to talk to each other. They exchange their public keys, which is common paint. They will add their own secret color in this case, and this will both turn into orange and blue. Now, they can then exchange the blue and the orange over a public channel because we can assume that separating this mixture is very difficult, and that's obviously when you look at it cryptographically, it could take years to decipher what the secret colors were. The nice thing is then, if you add red and Bob adds blue to the mixture, you will get a common secret, cryptographically speaking. So this is a very simple way of explaining basically what is happening. It helps me always quite a bit when I didn't focus on this for a while and I need to refresh how everything's working. So we're talking specifically today, or we're focusing a little bit on TLS, which is obviously used a lot around the internet and in the web. So TLS 1.2, we have a ClientHello listing a preferred list of cipher suites. And the cipher suites is just a set of algorithms that you can use to do the encryption. Then the server says hello back, and it will select a cipher suite. It will do key share and share the certificate. Then the client will do that as well, and then they're finished. You can do your GET request or whatever you want to do afterwards. So this is how TLS 1.2 works in a nutshell, obviously. So there's a lot of details left out. But it's important here to know that the client is sharing something, server is sharing something back, including the certificate, which we'll have a look at later. And yeah, this is basically the same as exchanging paint. With TLS 1.3, it goes a lot quicker, as you can see. So less arrows means more efficient, less latency. You can see here that the ClientHello already includes the key share, which is different from before, where the client was just first saying hello. Then the server, having that key, can immediately start encrypting parts of the server hello, which includes the certificate. And then afterwards, you can do the secure channel. So this is the difference between TLS 1.2 and 1.3. And again, it's basically exchanging paint, and the paint is hard to separate. Now TLS 1.3 obviously is becoming the norm, but it does bring some challenges with it. So TLS 1.3, because it immediately already has the key from the ClientHello, can start encrypting the parts of the server hello. So for example, the common name which is sent from the server in the certificate is actually encrypted now. And that means if you're doing anything on the network and you want to do any kind of enforcement with any kind of gateway like a IPS or a firewall or a web proxy or something in there where you want to make decisions on whether that traffic is good or bad, you can't really decide anymore based on the server hello what kind of traffic it is, what is the destination. Because obviously the big thing when you're looking at network traffic is where is it going. So when you have a network of your organization, you want to know where are these connections being made to. And that's now more difficult to do because we can only rely on the server name indication. And the server name indication, just to go back, is in the ClientHello. Now the server name or SNI can be spoofed because you can put anything you want in there as long as you control the server yeah, you can decide what to do when you receive that SNI. So, what if we send a fake SNI? Why would we do that? For example, website A is not allowed, so we're going to send an SNI that we're going to website B, but we're still going to same IP address. Now, you could browse to a forbidden gambling website, maybe. That's a little bit boring. But you could also have malware, which is connecting to a command and control server to either get an encryption key to start doing ransomware, or maybe to leak sensitive data. So this is probably where we should be worried about. So that's a little bit less boring. So yeah, that is what you can do now with TLS 1.3. Now there's also other protocols. So we have TLS 1.3 here. The usage is secure transport over the web, mainly. And then the goals obviously are a lower latency. It only uses modern cryptos. So if you look at a table with TLS 1.0, 1.1 up to 1.3, you'll see that only a few are left over in TLS 1.3, which you can actually offer. So it's a lot more secure and more simple. And obviously, it will have more. You can have more privacy against ISPs or governments or whatever. You also have DOE, not from The Simpsons, but DNS over HTTPS. So this basically means you're not doing a DNS request in plain text to over port 53, but you're doing a DNS request over HTTPS, as the name mentions, over port 443. And the obvious goal here is to encrypt your DNS lookup. And by doing that, you can't sniff the DNS traffic or have a look at the DNS traffic if you're in between. So this is also on the rise, and most browsers support this already. Then we have Quick, invented, I think, by Google. And this is used by Chrome a lot. And yeah, basically also is used for secure transport over the web. Similarly, it has lower latency. It can also do multiplexing without blocking, so it uses multiple UDP streams instead of one single stream. So there's also some advantages there. Now if we look at, for example, combining a couple of these protocols, you can see that TLS 1.3 and DNS, normal DNS, you can see that the TLS 1.3 connection basically bypasses everything. So whatever you have on your enterprise edge or your network edge, your ISP is not able to see it. Whereas with a DNS request, you usually go first to the local DNS server. That local DNS server sees, hey, this is public domain, I need to request the whatever you have configured there. So that usually goes to an ISP. Oops. So in this case, we can still use DNS to find out where this person wants to go. Now with DOH, it's becoming more difficult. If we were on the edge of a network, we're not able to do that anymore. So the only thing we can see now is, yeah, the ClientHello again, so the server name indication. So here's an overview of that, of all of the different combinations. But for today, this is at least important, that the server certificate is encrypted. And we'll see, we'll have a look mainly today at TLS 1.3, but it, yeah, basically goes for more. And we see at the bottom one with ECH, but that is not yet a norm yet, so that has only been proposed. So this was a brief introduction on how encryption works again. Yeah, I hope I didn't cover too much stuff that you might already know, but it's good to set the stage. Important to take away, encryption is good. It helps us keep our data private. But if you are using network traffic to do security, then yeah, obviously it poses some challenges, and it has been doing that for years, obviously, because it makes it more difficult to know where the traffic is going to. So, if I were an attacker and creating malware, which protocol would I use probably to make a connection outbound? Well, what you see is that the TLS 1.3 usage is increasing significantly overall, by the way, not just malware, but a lot of malware is more and more using TLS 1.3 and supporting it. And so it isn't necessarily bad, it's a good thing, I would say, but it does pose a problem when you are in the middle and you want to make decisions whether you want to approve something or not. Now, man in the middle has been a challenge for years as well already due to privacy and legal issues. Deploying it is difficult. It's expensive, so you need a giant box to do decryption. I'm not a fan of decryption at all. But I am a fan of stopping bad traffic going to command and control server. And also more things, obviously, so the lack of visibility, non-cooperating clients or cert pinning, all kinds of things which are problems for a man-in-the-middle decryption. So, obviously, it is a good thing, as I mentioned, to get more privacy. So it can protect you, depending on where you live, from your ISPs or your governments trying to look into the data, what you're doing. I think everyone in the world should have access to a private channel and search for whatever they want and not have people blocking certain things. So this is a good thing. Always be aware, by the way, that obviously you need to trust the service wherever you're going to because they can obviously see everything since the channel is terminating there. Now, there's a couple of things you can do with TLS. So you can hide, for example, using domain fronting. Domain fronting, you can see that the same CDN has multiple domains. And you can, for example, do a DNS request to example.com, do your TLS request with that server name, and you get it back. But then you use, in the actual HTTP request, you use something different as a host. A lot of CDNs are blocking this and looking for this. HTTP, goes against the HTTP protocol since these should match, but this is a way of doing some hiding yourself in this traffic. So here you see, by the way, a graph going up, and often graphs going up are positive. In this case, it's a graph that shows malware using 1.3 capable clients. The source here is ThreatGrid or Secure Malware Analytics, which is a tool from Cisco to analyze malware. And it also has a big database of threat intel that it offers. So you can see that this is going up. And it's been only going up since then. Here you can also see something else, which is domain faking. So here you see, again, what I mentioned. You can put something in the server name, and if you just pretend that you are capable of answering that, then you could technically use that as well to fake where you're going to if you're malware. What is seen though is that a lot of malware writers do use TLS 1.3, but they don't pay well attention into the cipher suites that they're using. So often you can catch them there as well in making mistakes that it's, for example, an expired certificate that they're using. All right, so we covered now also, basically the influence of encryption on malware. That's obviously important to take into consideration that encryption is good, but it's also good for malicious actors. So next, we'll talk about some things you can do to look at encrypted traffic and to find malware hiding in that encrypted traffic without decrypting it, obviously. So first off, all credits to two colleagues of mine, Blake and David McGrew. Blake has a PhD in computer science focusing on machine learning, and David McGrew has a PhD in physics, focusing on chaos theory. Very smart folks, and they created an open source project, which I'm here to promote today. And they also wrote 2 very interesting research articles. So I heard someone say earlier, if you're having sleeping problems, then this is a really good article to read. The first one is identifying encrypted malware traffic with contextual flow data. Very catchy, obviously. But it's a very interesting article on how you can use basically all of the metadata that is around there. For example, like things that are in the TLS ClientHello or DNS traffic, and how you can use that to enrich basically the information you have on that TLS connection. I can, by the way, post this, the link in the Slack afterwards to this article. They also wrote a new article as well, and this one is focused a little bit more on TLS fingerprinting, but it's similar concept, using more contextual data that is out there to decide on where this connection is going to. Is it a good connection? Is it a bad connection? If you simplify it. And again, here they look at information amongst others in the ClientHello. So the important thing here is that for both of these articles, they're basically assuming that the server certificate is not visible anymore. Now they created a project called Mercury, and it's an open source project, as I mentioned, and it's basically a system that can fuse together, billions or how many you have of real-world TLS sessions, and it grabs the information it needs to train a model. So you can use this if you have a big bucket of TLS sessions. You can use this tool to train a model, and that model you can use later to classify TLS sessions in either good, bad, and a couple of other things which we'll have a look at. So it is a Linux application, but they do also have a portable Python application as well. So all can be found on this link, but I'll share the links at the end in the Slack. The challenge is, if you're using TLS fingerprints, is that TLS fingerprints are very often the same for a lot of processes, so it doesn't really help you that much. For example, if you look at S-channel, which is I think the de facto Windows TLS module that you can use, a lot of different applications use S-channel, and if you're just using the default TLS settings, then the TLS fingerprint, and again the TLS fingerprint includes a couple of attributes from TLS, will be the same. So you can still not really use this to do a lot of smart decision making. And obviously if you're creating malware, then you probably also want to use the default settings for this. So it is actually important that if you have actual destination context, so where is this going to? For example, is it going to MicrosoftOffice.com? Is it going to WebEx? Or something like this? Is very important on top of just TLS information to make your decision on. So what did David and Blake do in creating this open source project? They thought of, all right, so what if we use different sets of information, fuse them together, and create a model that can then decide whether traffic is good or bad. So what they did is they used the fingerprint from the ClientHello packet, but they also used more network information, like the 5-tuple, so basically the source IP and port, and also the destination IP and port, as well as the server name indication. So they had quite a few things that they were using, and they can give this as input to the system. And they would like an output of a client process name. So what is the process that is initiating this TLS connection? Is it malware, yes or no? That's probably something nice to get as output. And they also wanted the operating system. So this is something that they're currently using. And they're all taking most of this out of the initial data packet, or IDP. And that is the ClientHello, which is unencrypted and includes a lot of information. And yeah, you can as I mentioned, get a lot out of this. What is, by the way, quite interesting is that you can also see from what they're using if it's a mobile or a desktop solution. So browsers tend to way more use heavyweight algorithms, whereas mobile applications obviously are more for performance, and therefore they prefer more efficient encryption. So that is already information that you can get out of there. What they're also looking into, and they've already built as well, but they still need to implement that into Mercury, is the sequence of packet lengths and time. The sequence of packet lengths and time, aka spelt, SPLT, is basically what it says. So how many packets are going back and forth as a function of time. And what they were noticing is that malware behavior, for example, when they're writing something to the disk, that means that there's no packets going back and forth. So that is sort of the length in between. Whereas communication with a command and control server obviously is a specific pattern. And this pattern differs a lot from normal browsing. So already based on this behavioral information, you can also have a lot of good information on whether something is good or bad. So they're still implementing this one. They did do it in a previous project, which I also have the link to as well if you're interested. Okay, so this is their plan. So how did they actually, how did they do this? Yeah, I did my best to explain some of the magic that they're doing. They're using machine learning, supervised machine learning. So basically, they have used a giant database or knowledge base that both includes the input and the output data of what they would like. So it includes both the fingerprint, etc. But the information is labeled, so they know this traffic is coming from this operating system, from this process, and it is safe traffic. Now, if you have a giant database of those kind of labeled sessions, which is, you can obviously also make yourself, then you can start training this model. So just a little bit more of background on the machine learning. So basically, they're giving it labels and data to create a classifier, and then later they're using data with that classifier to get the results. Just a little bit of background information. And in practice, it looks a little bit more like this. So they have the labels and data going in, they're doing some curation, massaging, and it's then going to train it, classifier comes out of it, but the results actually feed back into the curation. So this is also what this system is doing, and they're still continuously updating the model. So what did they then use? So how do you get this information? You could probably think. So what they did is they have data from a AnyConnect network visibility module, which is an agent which which you run on your MacBook or whatever on an endpoint. And this will give basically all of the information that is needed. So it gives the 5-tuple information about the destination. It gives a timestamp. It also gives the name of the communicating process. It also gives the file hash of the process executable, which could be malware technically, but this was the safe traffic, so this was usually a normal application. And it also gave the host operating system. For the malicious traffic, what they did is they used ThreatGrid, which again is that malware analysis sandbox, which I talked about earlier. They used this which is labeled because everything that comes out of a sandbox gets a score of if it's malicious or not. And they chose everything that has a score of 95 or higher to be positively labeled as malware. And they used thousands of TLS fingerprints out of this as well. And basically the same information, they just had to do a little bit of restructuring to get it in the same format, obviously. And there you go. They basically had one giant bucket of safe traffic and one giant bucket of malicious traffic. Yeah, that is what they used as a knowledge base. So here you can see the amount of TLS sessions on the top. So it was 13, I always need to, so we say milliard, I think that's billion in English, 13 billion. Please correct me if I'm doing the zeros wrong. Up to 53 million malware sessions. So they had quite a bit of sessions, and they're actually still feeding these sessions into the system. And every day they're still adding around 10 to 20 new unique TLS fingerprints with the information that I just showed on the previous slide. So the system was trained by fusing all of that data. So the data came both from an actual host as well as from the wire, so to speak. So they had networking data which they fused with this host data, and they matched that together in order to make the decisions that we want. Now, what kind of machine learning algorithm or statistical model did they use, you might ask? So for that, they used a quite famous one, which is a derivative of the Bayes model. So I'm not sure if people know the famous Bayes model, but basically it says the chance of A given B equals the chance of B equals A times chance of A divided by the chance of B. Now, we don't have to go into the detail of the statistics here, but this is just how it works. And basically the important thing is that you're taking certain data into account when you're making a decision. So A given B. So you're not just calculating the chance on A. Now I have one fun experiment here. What if there's an individual that has been described by a neighbor as follows: Steve is very shy and withdrawn, invariable helpful, but very little interest in people and in the world of reality. A meek and tidy soul, he has need for order and structure and a passion for detail. Now, is Steve more likely to be a librarian or a farmer? So who here says farmer? And who says librarian? Yeah. So most people in the audience said librarian here, which makes sense, to be honest. I also thought that at first, but and it's a very random example. It's from Kahneman and Tversky, but they invented, or they basically discovered that not a lot of people take all of the contextual information into account when they're making a decision. What they didn't take into account, and by the way, this QR code, I'll also share the URL, goes to quite a nice video that explains this. But basically, no one takes into account how many farmers are there in the world and how many librarians. So in this case, they said that there's only a few librarians and there's like 10 times as much farmers, which is probably true. So what are the odds of Steve being a librarian or a farmer? Well, you probably need to take into account how many farmers there are and how many librarians. So this just shows very simply how contextual information can help you make a better decision. And here you probably need to have a look at what is the chance that of a librarian given the evidence of all of the possibilities. And yeah, here you can take a look that, for example, 40% of all librarians are a little bit, yeah, as just described, and maybe 10% of the farmers are like that. But still, since there's so many more farmers, there's 20 more of people that are a little bit quiet than there are librarians. So the chance is a lot higher. Sorry for this little side tour, but that's, in my opinion, quite interesting to understand how this model is working. So this is the base model. The algorithm that Blake and Andrew used is the weighted naive Bayes model. And basically what this allows you to do is not just use contextual information, but you can also give it weights. So they use the two knowledge bases, which I described earlier, as training data. And they wanted to classify TLS sessions based on two features, the TLS fingerprint and the destination context. So that's going to be the input, and the output then are these three things: the client process name, the malware verdict, and the operating system. What they saw, for example, and that's why it's important that this is a weighted algorithm, is that the model actually performed a lot better. So they did some experiments there. If they gave a higher weight to the server name and the IP address to predict the process name, for example. So as you see here, the destination context actually includes multiple features. And if they gave some of those features more weight, then the model performed a lot better. And they can actually now predict with like 99 point, I think like a couple of nines, with certainty the client process name without having this information, by the way, right? So they just trained it using this data as labels, but now obviously the output is that, and the input doesn't contain it. Yeah, so again, the features here were the fingerprint and the destination context. The destination context includes the server name indication. And they are classifying this. And with that, we are nearing the conclusion of the session here today. So just as a recap, we saw how a little bit how machine learning works, how statistics work, and specifically how important it is to take all information into account when you're making a decision. And when you look at encryption, a lot of information is gone, so you need to become creative into what information is available and how you can then use that to find malicious actors on your network. So, to conclude, network encryption is increasingly important. It's helping us a lot to be more private, so that's a good thing. It is changing the way we do data security. It has already done that, so I think not a lot of security teams are still doing decryption. Maybe in some cases you can, maybe for inbound traffic, but especially outbound traffic is quite difficult to do decryption. So I think we should definitely not even bring that up anymore, especially because encryption has a reason. So why decrypt it? So it's changing the way we have to detect malware on the wire, obviously. There's a lot of solutions how you can detect malware on a laptop, of course. But in environments, in networks where you have a lot of IoT maybe, you can't place agents on all of those IoT devices. So there's still a lot of cases where you need to rely on network data to protect your network and protect the hosts in your network. So encryption-aware monitoring without decryption can enable us to identify a process, identify malware, and at the same time still be compliant, because what we can also see from this is, hey, are all of my hosts using the correct TLS versions here? I think there's, in the EU at least, there's these, obviously these financial regulations where, I'm not sure if they upgraded it to TLS 1.3 already, but at least anything below TLS 1.2 is not allowed. So if any host of on your network is doing that, it means you're not compliant officially. So there is actually a production implementation of this into a solution from Cisco. As you can see here, it will look at all of the connections, and it will see, hey, this is HTTPS, and we can decide whether it's malware or not. And also we can decide what the process name is. And it will give a confidence score on that based on that model that we're using. And here you can see a couple of statistics here. For example, what the process name was, and yeah, how high the malware confidence was. And again, this system is updating, right? So this is a self-learning system that keeps on updating itself. So whenever there's new applications being made or new malware being made, the system can update itself, and the model will then hold all of those unique combinations of information. With that, we have reached the end of my presentation here today. And I do have some more resources for you. And again, I'll post these in the Slack channel so that yeah, you can reach them yourself as well. And I would definitely recommend taking a look at this open source project Mercury. You can just have a look at it, download it, and play around with it. The thing is, you do obviously need a way of collecting those TLS sessions to feed into it. But yeah, it's yours for the taking. And again, read the research article. I'm not sure who here is from Norway or not, but if you're taking a flight home or a train home, by the way, then maybe check it out as well. Here's some information how you can reach me. You can email me, Twitter me, send me a LinkedIn message or GitHub, yeah, a pull request or whatever. And yeah, with that, I would like to thank you very much for your time.
Could you say a few words on what kind of classification models are being used in this?
On what kind of?
Classification models. Like what kind of machine learning? What basic algorithms are being used?
Yeah, so yeah, basically what they're doing again is using the weighted naive Bayesian algorithm, which is an algorithm which you can use yeah, give certain features that you're using weight, and with that they can then control how the output is better. So the classification is then more accurate. So that is the algorithm which they're using. It's called weighted naive Bayesian algorithm. I don't know the minor details on it, but that's the big picture of what they're doing. Yeah.
Is there like statistical representation of false positives?
Yes, that's a good question. So obviously that is a big enemy of automation is false positives. So what they actually, so if in the research article, they have an overview of this. And well, they were obviously able to train the model with a very low amount of false positives, almost zero. And then what they did afterwards is they tested the model based on traffic which was still labeled, but they didn't use in the training. And I think they, yeah, I forgot the amount of zeros, but they were able to reach a very significant low amount of false positives, making this an actual system you can use in real life. Yeah, but it's a really good question. Other questions? No? All right. Well, thanks again, and yeah, enjoy the rest of the conference.